In our first video, we tried to get comfortable with what's called the standard matrix for a linear transformation, where we're just seeing what happens to the vectors e1, e2, e3, and so on, however many it makes sense depending on what the domain of your transformation is. So like if the domain is R3, for example, you're going to have e1, e2, and e3 that you need to run through the transformation to be able to figure out what those are, and then you have the standard matrix. In our second video, we're going to begin looking at the rotation matrix. It turns out that the rotation matrix is defined in this way, and I wanted to go, even though this is something that's gone through in the textbook, I think it would be helpful to just kind of see this, where this comes from. It basically comes from our basic knowledge of trigonometry is where this comes from. Okay, so let's try to motivate this here. So we basically want to figure out what happens with E1, right? E1, which is 1, 0. Let's see what happens to this vector under a rotation. So suppose we wanted to rotate this by an angle theta. Let's calculate the resulting image. So let me go ahead and draw a picture. Okay. So if we are taking the vector 0, 1, which starts right here, now imagine rotating this counterclockwise. This is what we're talking about here. We're rotating this counterclockwise through some angle phi. Let's just assume that the angle phi is such that we would end up in the first quadrant when we do this. So right here is the angle phi. Oops. There's the angle phi that we've rotated by. So off of this we can form a triangle, right? And the triangle is going to have an x distance of x1 and a y distance of x2. And since we were starting originally with 1, 0, there is an associated unit circle with this. Right here. So this is the unit circle. This distance has to be 1. Okay, so we are starting at 1, 0, rotating through an angle phi, like we've indicated right here, and here's where we end up. So we end up at some location x1, x2. Right there, which is right here. So there's the vector. That's where we end up at. Okay, so let's go ahead and just use some of our basic trigonometry. We know that sine of phi is going to equal x2 over 1. So this tells us what x2 is. Cosine of phi, on the other hand, is going to be x1 over 1. So we figured out what x1 and x2 are. So the resulting image is, so here's what we found. We found that t of e1, that the transformation is that's going to rotate any vector through an angle phi. We'd like to first figure out what happens to e1. Okay. So the result is the vector x1, x2, where specifically x1 is cosine of phi and x2 is going to be sine of phi. Okay, so we found t of e1. Once we find t of e2, then we'll have what the matrix is going to be. Let's go ahead and do that. Okay, so e2. E2 is 0, 1. All right, so imagine we're starting at 0, 1, which is up here. We're rotating through an angle phi, which isn't going to move us more than just one quadrant. It's only going to move us into the second quadrant. since the angle phi was less than 90 degrees, or pi over 2, then this is going to take us into the second quadrant, right here. Yeah. Well, let me put this in first. Okay. Okay, so we're going to have some distance minus x1 that we went in this direction, and then x2 that we've gone vertically, sort of to our triangle. And again, there's going to be a unit circle associated with this. Because we started at 0, 1. Rotate it, the hypotenuse is 1. So we can do just like before, we can use some trigonometry here. If we take sine of phi, that tells us that we end up with basically minus x1 over 1. Cosine of phi is going to give us x2 over 1. Right? So then from there, if we wanted to figure out what t of e2 is, well, that's just what t of 0, 1 is. And what does t do? T rotates counterclockwise by an angle phi. So we figured out what the result is. The result is we're going to end up at x1, x2, which is right here. Okay, so we'll end up at x1, x2, where specifically we end up with we end up with minus x, or hold on, back up. Yeah, so x1 would be minus sine of phi, and then x2 is going to be cosine of phi. There we go. Okay, so therefore we can write down what the standard matrix for this linear transformation would be. The standard matrix is going to be t of e1, t of e2, put in as columns. And specifically, they are t of e1 is cosine of phi sine phi. That's what we got for that. And then we have minus sine phi cosine of phi for the second column. And notice that is what the rotation matrix is in general. Now we only work this out for an acute angle phi, where the angle is between 0 and 90 degrees. It makes no difference if you choose a larger angle. Your pictures are going to change slightly. Like if your angle was large enough where you would go into the second quadrant or the third or the fourth, but it's basically the same idea. The same argument, you'll end up with the same matrix if you go through that. But just for simplicity here, I set it up where we had an acute angle. So that's how you find, or that's where the rotation matrix comes from. All right, let's go ahead and try to summarize some of these transformations, since we've had 2 sections about this now. So some of these we've touched on, some of these we haven't. This is just some tables that I've grabbed from the textbook here that we're going to be going through here. So so this matrix here, this standard matrix, 0, or if you have zeros off the diagonal and down the main diagonal you have a 1 and minus 1, that is going to give you a reflection over the x1 axis. Over the x2 axis, if you had minus 1, 1 down the diagonal, zeros off the diagonal, that would reflect you over the x2 axis. If you wanted to reflect over the line, basically y equals x, or x2 equals x1, if you will, then you want zeros down the diagonal, 1s off the diagonal. That's going to do that. That's going to accomplish that. A reflection through the line y equals minus x, or x2 is equal to minus x1, is accomplished with 0, 0 down the diagonal, minus 1s off the diagonal. And then finally, a reflection through the origin is accomplished with this standard matrix right here. If you recall from the previous section, we saw this as an example. We worked this out. Okay, so the next page here. Let's talk about what are called contractions and expansions. If you want the vectors to be kind of expanded horizontally like we see right here, you would want K1 down the diagonal, zeros off the diagonal. And it's being kind of expanded by that factor K, where K here is going to be, I guess if you wanted to expand things, K would be bigger than 1. If you wanted to be a contraction, then pick a fractional K between 0 and 1. And similarly, if you have 1K down the diagonal, zeros off the diagonal, you can have a vertical expansion and contraction. All right, so let's talk about shears. We've actually done both of these shears. We did an example in the last section and then an example in this section where we had both kinds. So 1, 1 down the diagonal, 0K off the diagonal, that is a horizontal shearing. If you have K negative or K positive, it's going to shear either to the right or the left. A vertical shear is if you have the K down in this lower position instead and then the 0 up there. And again, if K is positive or negative, it's either going to be sort of shearing up or shearing down. Projections, we did one of these. So basically, if you have a 1 in this position, zeros everywhere else, that's going to be a projection onto the x1 axis. If you put the 1 instead down in this lower right position, it's going to be a projection on the x2 axis. And then finally, we just talked about in the previous example, we had a rotation matrix. Okay, let's go ahead and stop right here with this video. I think at this point you could have already done problem 1 from the MyLab homework assignment. I think you can do problem 2, problem 3, problem 4. And I think we'll kind of stop there. Yeah, I think the first 4 problems you can do at this point. Oops.